When introducing Switching Activity Interchange Format or SAIF file, it's important to highlight that modern digital circuits, whether small IP blocks or large SoC, consume power primarily due to signal switching. Every time a node transitions between logic states, it charges and discharges capacitances, creating dynamic power consumption. The challenge engineers face is accurately estimating this power, because real switching activity depends heavily on how the design behaves under realistic workloads. This is where the SAIF format becomes essential. SAIF offers a compact and standardized way to capture the actual switching characteristics from simulations, including how often signals toggle and the probability of signals remaining at logic 0 or 1. Unlike traditional waveform dumps like VCD, which can be very large and slow to process, SAIF file summarizes the key power-related behavior into a lightweight text format that EDA tools can quickly read. This efficiency enables power estimation tools to perform meaningful analysis without being slowed down by large simulation traces. Switching Activity Interchange Format file also functions as a bridge, connecting various tools in the design flow, simulation, synthesis, and power analysis, ensuring that each tool uses consistent and realistic activity data. Ultimately, SAIF enables more precise early-stage power modeling, supports iterative power optimization, and assists designers in identifying power hotspots or unnecessary switching very early in the design cycle, well before physical implementation. The key features of a Switching Activity Interchange Format or SAIF file are discussed here. It helps to explain why these elements are important in a real design and verification process. A SAIF file mainly shows how the design behaves dynamically, and each signal's toggle count, static probability, and hierarchical organization play a unique role in increasing the accuracy of power analysis. For example, the toggle count reveals how often a signal switches, which directly impacts dynamic power consumption because each transition charges or discharges circuit capacitance. Static probability is equally important because it shows how long a signal stays at a steady logic level. This helps power estimation tools identify leakage power contributions and understand signal biasing within the design. The hierarchical structure in Switching Activity Interchange Format files allows power analysis at various levels, from the top-level architecture down to individual submodules or nets, which is crucial for detecting localized power hotspots and implementing targeted optimizations. Switching Activity Interchange Format or SAIF files can be generated from synthesis, with activity annotated or after simulation, and the timing of their generation influences the quality of power estimation. Switching Activity Interchange Format file produced after RTL or gate-level simulation with realistic test benches offers the most precise depiction of actual switching activity. This makes SAIF an essential component of modern low-power design methodology because it helps designers make informed decisions early, validate power assumptions, refine clock gating strategies, and ensure that the final silicon operates within expected power limits, even under real application conditions. Here is the sample Switching Activity Interchange Format file structure. It's important to help the audience understand not just what each field means, but why the structure is organized this way, and how engineers use it during power analysis. A Switching Activity Interchange Format, or SAIF file, begins with header information that defines the context of the recorded switching activity. Details such as the SAIF version, design name, simulation date, tool vendor, simulation program, timescale, and total simulation duration. These fields act like metadata that ensure all downstream tools interpret the activity information consistently, especially when power results need to be correlated across different stages of the design flow. After this header, the file transitions into a hierarchical view of the design, starting with the top-level instance and progressing into submodules. This hierarchy is important because power analysis rarely considers only top-level figures. Engineers want to identify which specific blocks or nets contribute most to switching activity, and a hierarchical Switching Activity Interchange Format, or SAIF, enables the power tool to break down consumption at the module, instance, or even net level. Inside each instance, individual nets are labeled with data such as toggle count, switching activity, and static probability, providing the power engine with insights into how often each node transitions and how it behaves statistically over time. For example, a clock signal with a high toggle count but a 50% static probability indicates a balanced switching pattern, while a reset signal with low activity indicates infrequent transitions. When analyzing the signal level details, shown in this example, Switching Activity Interchange Format, or SAIF snippet, it's important to emphasize how this information directly aids in understanding and optimizing power in a digital design. Each signal, such as data in or data out, is labeled with metrics that describe its actual dynamic behavior during simulation. The toggle count, switching activity, and static probability become especially useful for estimating leakage power and understanding the biasing tendencies of different nets. These parameters together enable power analysis tools to develop a realistic profile of where energy is being consumed in the design. Organizing the SAIF in this modular and descriptive way allows engineers to trace hotspots, validate power intent, and accurately document real simulation activity. This structure highlights the systematic and user-friendly characteristics of Switching Activity Interchange Format, or SAIF, making it vital in any power-aware digital design workflow.